We will continue our discussion on properties of solids. We will talk about vapor pressure first. Vapor pressure is the tendency of a substance to go from the liquid or solid into the gas phase, so to evaporate. How easily does a substance evaporate into the gas phase? Now let's think about what is happening. If I have something in the solid phase or liquid, how easy it is for those molecules to then overcome intermolecular forces between it and other molecules in the solid that hold the particles together and go into the gaseous phase. That the vapor pressure is going to be the pressure of the gas that is formed by these molecules that escape from the solid and go to the gaseous phase. You can then determine that the stronger the intermolecular forces that hold those molecules or atoms or whatever they are, the particles, in the solid phase, the smaller the vapor pressure is going to be, because fewer molecules are going to be able to escape and enter the gaseous phase. The weaker the intermolecular forces that hold the particles together, the greater the tendency of those particles is going to be to enter the gas phase. So the easier it is for them to separate themselves from other particles that are attracted to them and enter the gaseous phase. So vapor pressure is inversely related to intermolecular forces. The stronger the intermolecular forces, the lower the vapor pressure. The weaker the intermolecular forces, the higher the vapor pressure. Here's a sample problem for you to try. At negative 125 degrees, both of these molecules are solids. Determine which compound has the lower vapor pressure at that temperature. The first thing you're going to do is determine, obviously, which one will have the stronger intermolecular force. So you're going to have to do a little bit of Lewis dot structure first, and then determine whether the molecule is polar or not polar, and that will tell you whether it has just London dispersion forces, or does it have dipole-dipole interactions, or does it have hydrogen bonding. That will determine the strength of the intermolecular force, and therefore the vapor pressure as well. Let's move on and talk about melting point. Melting point is the temperature at which the solid melts, right? We know that. Solids that have stronger intermolecular forces will melt at higher temperatures than those that have weaker intermolecular forces. Here is a graph that shows the different groups. So group 14, group 15, group 16, and 17 in the periodic table, and their corresponding melting points. Note that these are the same type of molecules. They're bonded. The only thing that's differing is the first element that's listed in that molecule, and they're elements of group 14, for example. So carbon tetrahydride. This is silicon tetrahydride. This is germanium tetrahydride. This is tin tetrahydride, right? And you can see how they increase with increasing molar mass. And we know that this is true because we also know that intermolecular forces, especially London dispersion forces, they increase with increasing molar mass. However, when we go to group 15, 16, and 17, we see something different. The first elements that are listed, so HF, NH3, H2O, those have the highest melting points as compared to whatever elements come after them. Well, why is that? we know that even though these molecules are becoming polar, so they have higher melting points than these because they have dipole-dipole interactions on top of dispersion forces, these three molecules here, H2O, NH3, and HF, have hydrogen bonding on top of dipole-dipole interactions. And so you can see that because these three molecules have the stronger intermolecular forces, they also have the higher melting points as compared to molecules that are very similar to them, like H2O is similar in shape to H2S, H2SE, H2TE. These are polar molecules as well, but they don't hydrogen bond like water does. And that's why water has stronger intermolecular forces and higher melting point. Same thing can be said for NH3 and HF as compared to similar molecules in their group. Here's the melting point of some solids. There's the solids that are listed. This is their molecular mass, so how much they weigh per mole, grams per mole. These are the types of intermolecular forces that you find in these molecules. And you can see how different their melting points are, how much they vary, depending on what type of intermolecular forces and how large their mass is. Here's another sample problem for you to try. Place the following substances in order of increasing melting point. Here's the substances. You will first need to determine the types of intermolecular forces that are found in each of these, and that will determine which one has the lowest melting point, the next highest, and the next highest. So give this a try.